but we're going to try to knock it out. So we're trying to get to central limit theorem. When we get there, we're done. All right. They may not be posted, Emily, so dang. Just follow through. If you want a copy, text your dad and tell him to come get them from me so I don't forget. He's leaving today at some point for basketball. So tell him to come get them. And then everybody else, before we finish, I'll put them up. I'll have to scan them in because that's why they're not up there. All right. I tried to give everybody that was in class a copy, so I apologize. I didn't even think about it. I should have scanned it in yesterday. But all right. So I am recording. Sample populations arise most often when we're interested in categorical variables. So remember, like the color of the M&Ms, we were talking about that. That's categorical variables. So we then ask questions like, what proportion of U.S. adults have watched Survivor, or what percent of the adult population attended church last week? But when we record quantitative, which is household income, lifetime of car brake pads, blood pressure, we're interested in other statistics, such as the median or the mean. Or the standard deviation of the variable. The sample mean, or X bar, is the most common statistic. Remember, it is a statistic. Don't forget statistics and parameters. Computed from quantitative data. This section describes the sampling distribution of the sample mean. We're going to skip over the activity. We don't need it. And we're going to go on down to the example. Okay. All they did was doing more shape, center, and spread from a dot plot. So we're okay right there. We're going to move on. Okay. So a first look at the sampling distribution of X bar. The figure below is a histogram of earnings, and it's actually on the next page, but we'll get to it in a minute. Of a population of 61,742 households that had earned income greater than zero in a recent year. As we expect, the distribution of earned incomes is strongly skewed to the right. And very spread out. So let me see if I can show you guys this one. So it's this, it's on the next page, but it's this right here. So just looking at it really quick. The right tail of the distribution is even longer than the histogram shows because there are too few high incomes for their bars to be visible on this scale. We cut off the earnings scale at 400,000 to save space. The mean earnings for these 61,742 households was 69,750. All right. So again, why is it right skewed? If you guys think about it, there's less rich people. Okay. So more of the data is going to be towards the lower end of it. Take an SRS of 100 households now. The mean earnings in this sample is 66,807. So I'm going to stop right there for just a minute. Look at the difference. Both of these are means. What's the difference? And why am I using mu here and X bar here? I don't know what today is. Nobody has literally been answering any questions. What's the difference in the notations? Yeah, that's it. So this mean is from the direct population of 61,000. This mean is a sample mean from 100 households. So this is a sample. So that's the only difference. They're both means, One is just from the population and one is from the sample. Okay, so we need to know the difference between those two notations. That's less than the mean of the population. Take another SRS of size 100. So if we're doing that chip thing, we put the chips back in and now we're taking 100 more out. The mean for this is going to be still X bar because it's a new sample. 70,820. So that's higher than the mean of that population. So that was higher than that mu value. What would happen if we did this many times? The second figure is a histogram of the mean earnings for 500 samples. 500 samples, each of size 100. So look at what it did. The scales and the figures are the very same for easy comparison, although the distribution of individual earnings is skewed and very spread out. The distribution of the sample means is roughly symmetric. And much less spread out. Why is that? What's our rule?
Bigger sample.
And the more samples we take, the less variation. Same thing, same thing. All right. So both distributions are centered at mu equals 69,750. So once we took that 500, it pulled that mean from the first one we got to the 70,820. It centers it up on that actual population. So the more we take, the more it's going to be close to that population. So what does this say? This example illustrates an important fact that we make precise in this section. This is important. Averages are less variable than individual observations. So one sample has huge variation from the mean. Where if we take an average of a bunch of samples, it'll be closer to that actual mean. So it'll have less variation. The sampling distribution of X bar, mean, and standard deviation. So those of you that don't have notes, those little starred things, those are what you want to know. Okay, so if you don't get anything out of this, get the little starred stuff, get any formula. All right, so that's the super important stuff. The figure above suggests that when we choose many SRSs from a population, the sampling distribution of the sample mean is centered at the population mean. And remember that's mu. So those of you that don't have notes, you may want to write population mean equals mu. And is less spread out than the population distribution. So here are the facts. So suppose that X bar is the mean of an SRS of size n, drawn from a large population with mean mu and standard deviation, the population standard deviation. The mean of the sampling distribution of X bar is mu sub X bar equals mu. So they're the same thing. The mean of the sample is the same thing as the mean of the population. However, the standard deviation of the sampling distribution of X bar is the population standard deviation over the square root of the sample size. This is only as long as the 10% condition is satisfied. Remember that the sample has to be less than 1/10 of the population. So when we multiply the sample by 10, that number cannot be greater than the population. All right, and we're gonna go back over these. And guys, when I upload these for you, I'll upload with mine filled in. So I'll do this set so that you guys don't have to go back and fill it in. All right. So the behavior of X bar in many repeated samples is much like that of the sample proportion p hat. The sample mean X bar is an unbiased estimator of the population mean mu. Two more bullet points in this section. The values of X bar are less spread out for the larger samples. Remember, the larger sample, the less variation. Their standard deviation decreases at a rate of square root n. So you must take a sample, remember we said 4 times as large to get the standard deviation of the distribution of X bar in half. So the square root of 4 is 2. Cuts it in half. You should use the formula, population standard deviation over the square root of n for the standard deviation of X bar, only when the population's at least 10 times as large as the sample, which is the 10% condition. Okay, and we're going to go over all of this again. This is just giving you some background. Notice that these facts about the mean and standard deviation of X bar are true no matter what shape the population is. So we don't care what shape it is, you still have to do that. So this next example says this wine stinks, the mean and standard deviation of X bar. We're just going to find the mean and standard deviation. So sulfur compounds such as dimethyl sulfide, DMS, are sometimes present in wine. DMS causes off odors in wine. So winemakers want to know the odor threshold, the lowest concentration of DMS that the human nose can detect. Extensive studies have found that the DMS odor threshold of adults follows a distribution with mean. What does mu mean again? Nope. Population. Mu is your population. Micrograms per liter, and standard deviation of 7. So remember, population is the O looking thing, and then sample standard deviation is S sub X. Okay, so don't forget that. Suppose we take an SRS of 10 adults. That's important. That gives us what? N equals what? Perfect. And determine the mean odor threshold X bar for the individuals in the sample. So it says, what is the mean of the sampling distribution? And it says, explain. So remember, our formula said the mean of X bar, this is your explanation right here, is the same thing as the population mean. What was our population mean? And why can we do this? This is your explanation. Because X bar is an unbiased estimator. That's it, that's part A. B, said it's what is the standard deviation of the sampling distribution of X bar. Remember, to find the standard deviation, we have to check the 10% rule. So the first thing we need to do is check the 10% rule or 10% condition. The way we do that is 10 times N has to be less than or equal to the population. In this case, our N is 10. Is 100 less than the population? What's our population? What is our population though? What is the actual like words? What do we take an SRS of? 10 adults. So 100 adults. Can we have more than 100 adults? Yes or no? Yes or no?
Yes.
No, we can't have more than 100 adults. There's not more than 100 adults?
Oh, okay, yes.
Yes, okay.
Does it mean like more adults like in the world? Like I'm confused.
Mhm.
over-
Uh-huh. Because they're just studying adults, their smell. That's it. So it can be any of them. A lot of times it'll say like US adults or adults ages 21 to 36 or something like that. So how many are there is basically what it is. There are more than 100 adults. So it passes the 10%. So then we find the standard deviation. Remember our formula for standard deviation of the sample is the population standard deviation over the square root of n. It told you in there that the population standard deviation was 7 and our n was 10, so 7 over the square root of 10, which is 2.214. Also, don't forget how to say the mean and the standard deviation if they ask you to, okay? Justify what it means or explain it in context of the problem. So if they ask you to explain in context of the problem, your mean, what's this one going to be? Average micrograms per liter in SRSs of size 10. That's all you got to remember. SRSs of size 10. So this would be typically varies from the mean 2.214 and make sure you have SRSs of size 10. Okay. All right. So just wanted to review that. I don't know if that comes up. I just wanted to throw that out there to remind you. All right. So can we confirm the formulas, the mean and the standard deviation of X? So again, those of you taking notes, this is going to be where we're trying to validify all of our formulas, okay? So that's what they're doing. So we're going to choose an SRS of size n from a population and measure a variable x on each individual in the sample. Call the individual measures x1, x2, blah, 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 all the way to xn. It should say if the population is large relative to the sample, listen, don't judge. We can think of these x's as independent random variables, each with mean mu and standard deviation, because your x bar is going to equal 1 over n, x1 plus x2, all the way to plus xn. We can use the rules for random variables, should say from chapter 6 to find the mean and standard deviation of x bar. So that was Aaron and Pete's Jeep tours. You guys remember that one? Okay. So we said that we could get the total by doing x1 plus x2 plus all the way to xn. And we found out that x bar was the same as 1 nth times the total. All right. So using the addition rule for mean and variances, we've done that again, Aaron and Pete's Jeep tours. To find the totals, we did the mean of the first one plus the mean of the second one, all the way to the mean of the last one. But what do we know about the sample mean? It's the same as what? Yeah, so each one is going to be population plus the population plus the population, so on and so forth. And an easier way to do that is just multiply it by the number of times that happens. So n times mu. So if we had 20 of these mu's, it would be 20 times mu. to do the variance totals, you did the variance of the first one plus the variance of the second one. Remember, we had to do variances. You can't add standard deviations. You have to add variances. All the way to the variance of the last one. Again, it's going to be the same. So we have a variance plus a variance plus a variance, and we keep going, which gives us n times the variance. So then from there, how do we find the standard deviation? Mm-hmm. So to find the standard deviation, we take the square root of n times the variance. Square root and a square cancels out, so the variance will come out and become the standard deviation, but the n will not come out because it's not a square. Okay, don't freak out too much. That's just general math, but when you put it with letters, it looks really weird. Okay, so don't stress too much about it. It's just showing you how they derive the formulas. Because x bar is just a constant multiple of the random variable t, mu of x bar is 1 over n times mu of the total. Remember that mu of the total from that top part right here was n times mu. And then remember, these n's will cancel out when we multiply, and we'll just get mu. So it's just showing you why the mean of the sample is the same as the population. So mathematically, you don't have to do the formula. You don't have to work it out. They're just telling you, here's why you know it's this, okay? Same thing on the next one. Standard deviation of the sample is 1 over n times the standard deviation of the population. So 1 over n times what we got up here. And then this is where it gets complicated to put this n back in. To be able to take it out, we have to double it to put it in. So what you're going to have is that n is this one here. To put this one inside, we have to square it. We have to square it. These will cancel each other out and just leave square root 1 over n. We can rewrite this big square root as 2 small square roots. Square root of 1 is 1. We cannot take the square root of n. And then if we multiply it together, there's where your formula comes from. So what do you need to pull from this? Not all this crap. Here's what you need to know. Just what we wrote before, and I'm actually going to write it down at the bottom. The population mean and the sample mean are the same. And then the standard deviation you found by taking the population standard deviation over the square root of n. These are the 2 formulas that you need to know, okay? All that crap above it is just how they derive them. So you don't have to memorize that. It's just showing you mathematically how it works. This is what you need to remember. So we have described the mean and standard deviation of the sampling distribution of the sample mean x bar, but we have not talked about its shape. That's because the shape of the distribution of x bar depends on the shape of the population distribution. In one important case, there's a simple relationship between the 2 distributions. Two more pages, we're done. Okay. This one is just this fill in the blank. Okay. So it says, here's an activity. Professor David Lane of Rice University has developed a wonderful applet for investigating the sampling distribution of X bar. It's dynamic and it's fun to play with. You can use this to play around with different distributions, but here's what you'll find. So you don't have to do it. Here's what you'll find. Note takers, this is important. If the population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what the sample size is. Sampling distribution of a sample mean from a normal population. Suppose that a population is normally distributed with mean mu and standard deviation. Then the sampling distribution of X bar has the normal distribution with the mean mu and the standard deviation, provided that the 10% condition is met, of the population standard deviation over the square root of n. So this is if it's normal. But what do we always got to check when we find the standard deviation? 10% condition, okay? We already know the mean and standard deviation of the sampling distribution. All we have added is the normal shape. Now we have enough information to calculate probability. Remember when we calculate probability and it's normal, we're using normal CDF or normal PDF. So that's what it's getting you to. So that state, plan, do, conclude. All of this other stuff has been during the plan, the 10% rule, all that bins, all that stuff, so that you can actually calculate. Okay, so that's what we're doing. Got it? All right. So now we have enough information to calculate the probability involving X bar when the population distribution is normal. So everything you've done comes right back again. Okay. There is no state plan due conclude today. Okay, so we're just doing easy stuff. It's really quick. Tells you exactly what to do. All right, so here's some examples. The height of young women follows a normal distribution with mu equal to 64.5 and the standard deviation of 2.5. Find the probability that a randomly selected young woman is taller than 66.5 inches and show your work. And then part B, we're going to find the probability that the mean height of an SRS of 10 young women exceeds, make sure you read that, exceeds 66.5 inches and show your work. Okay. So note takers, I would take this. Okay. This is something I'd definitely write down. So we're going to find the probability. So we need to make a probability statement. P, and then our parenthesis, is taller than 66.5 inches. So how do we write that?
66, X is greater than.
Perfect. It already told us that it was normal. So I know I'm going to use normal. PDF or CDF? Why CDF? Because it's an inequality. Remember, P is perfect or equal to. It's going to ask us about lower. It's going to ask us upper. It's going to ask us our mean and our standard deviation. Make sure when you do this on your AP exam and on your tests, you define what all these are, okay? So what would your lower be?
66.5.
We want bigger than 66.5, so the lowest we can go is 66.5. What's our upper going to be? A big number, because it doesn't define an upper. Our mean was 64.5, and our standard deviation was 2.5. Where do we go in our calculator to do that? Second bars, just to remind you. We're doing CDF. Our lower was 66.5. Our upper was 10,000, 64.5, and 2.5, and we get 0.221, or sorry, 2119. Tell me what this means. It doesn't ask you to, I'm just asking you.
25% eliminate color would be 66.5 inches.
There's a 21.19% chance that a randomly selected young woman is taller than 66.5 inches. Okay, remember how to justify it or define it. All right, look at part B. Find the probability that the mean height of SRS of 10 young women exceeds 66.5. So now what are we doing compared to what we were doing? What's this compared to this?
We have a number of it,
We have a what?
limit on the number.
Right, we have an SRS of 10, which puts us n equals 10, right? So that means we're dealing with a sample now. So we have to do the sample mean and the sample population, sample mean and the sample standard deviation into our normal CDF stuff, okay? So we got to change our mean and standard deviation. Everything else is going to be the same. So we need to find the mean of the sample, which we know is the same as the mean of the population, which was, okay, so that one will not change. But our standard deviation of our sample, how do we find it? Can I just go ahead and find it? Yes, check the 10% rule. Or a 10% condition. I don't care what you call it, okay? So we have to do 10 times, what was our population? I mean, our sample size? 10, which is 100. Is there more young women than 100? Yes, there are more than 100 young women to choose from. So now we can do our standard deviation. What was our population standard deviation? 2.5. Our N was 10. Somewhere you may want to, this defines it, right in the formula defines it. If you just write numbers, that doesn't define it. So if I would have just went like this and skipped that part, you're going to get less credit for this, okay? When I write the formula, I get full credit, all right? This will give you 0.79. This time, check out our probability statement. This time it's going to be X bar because we're talking about the sample. We want to exceed, so greater than 66.5. So it's the same thing. We're just changing our standard deviation. The mean does not change because it's the same as the population mean. So we're going to do the same thing, normal CDF. Your lower is still going to be the same. Your upper is still going to be the same. Your mean of the sample is going to be the same. But your standard deviation of the sample is going to change to 0.79. Now when you put it in your calculator, 0.0057. So there is a less than a 1% chance that the mean height of a young woman from an SRS of 10 exceeds 66.5. So just make sure that you write that definition down, the SRS of 10. Okay. This next page is literally just fill in the blank. There's nothing to add to it. And then we got one more page after that, okay? So the fact that averages of several observations are less variable than individual observations is important in many settings. For example, it is common practice to repeat a measurement several times and report the average of the results. Think of the results of n repeated measurements of an SRS from the population of outcomes. We would get if we repeated the measurement forever. The average of the end results, or the sample mean X bar, is less variable than a single measurement. Last page, and it's just examples. Okay, check your understanding. All right. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal. So that's important. We're going to use normal CDF or PDF. We have a mean, so that's mu of 266, and a population standard deviation of 16 days. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days and show your work. Okay, so this is a randomly chosen woman from the population. So we're using our population stuff. Until it tells us SRS, which it does in part 2, till it tells us that, we keep this same mean and the same standard deviation. Okay, so number 1, we want the probability that X is what?
Greater than 270.
Good. So how are we going to do that? It said it was normal, so we're going to use
Normal CDF.
what's your lower going to be?
270.
What's your upper going to be?
High number.
A really high number, 10,000 is what we usually choose. What's your mean?
266.
Standard deviation, which gives you 0.4013. Then it says, suppose we choose an SRS of 6 pregnant women. Let X equal the mean pregnancy length for the sample. So number 2, we're doing an SRS. SRS of 6 means that n equals 6. So we're throwing a new number in there, so that's how you know it has to change. What do we know about the mean of the sample? It's the same as the mean of the population, which is? Why is that the case? What did I tell you earlier? Why can we use the same thing?
Oh, I'm fine.
Uh-huh. It's an unbiased estimator. 3 says compute the standard deviation of the sampling distribution of X bar. They will not tell you this all the time, but what they're trying to get you to understand is every time you try to find that standard deviation, check the 10% condition. So the 10% condition is what we need to check first. We do that by 10 times the sample. So our sample size was 6. So 10 times 6 is 60. Do you think there are more than 60 pregnant women in the population?
Yes.
And you can write that, more than 60 pregnant women in the population. What's our formula for our standard deviation of X bar?
The standard deviation over the square root of n.
Perfect. So our population standard deviation was 16. Our n is 6, so 16 over the square root of 6 is 6.532 days. This is a good example because if you take like a regular population, every pregnant woman has a typical gestation period of 266 days. If you take 6 of those women, we still have the same gestation period. Okay, doesn't matter that we took a sample, it's going to be the same. Nothing's going to change about that. Okay, just because we took less people doesn't mean it's going to make your pregnancy less. Make sense? Okay, so there's a good way to see that. All right, number 4, last thing, find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. Show your work. So we're doing the probability. What do I write instead of X? X bar exceeds 270. Remember, the only thing that changes is the standard deviation, okay? So we're going to do normal CDF. We want 270 as our lower, 10,000 as our upper. Our mean stayed the same, and our new standard deviation for the sample was 6.532, which gives us 0.2709. Okay. One more time. When we pick one pregnant lady, we have a variability of 0.4. When we pick 6 pregnant ladies, we have a variability of 0.2 or 0.3. So remember, the more we pick, the more the sample size, the more samples we take, the less variability we have. And that's it. Is everybody good? All right, Zoomers, stay on. I'm going to stop sharing, stop recording.